All right. So we're doing the rest of chapter 2 today. Chapter 2 is on more on stuff on, I don't know, what the hell did I call chapter 2? Data. That was the fancy name I gave for it. We're organizing data. And we showed some ways of doing the organization of data in StatCrunch. If you guys remember, we did bar plots and pie charts and stuff like that. I found if I elevate it up like this, it gets the right light. Bring that another day. Apparently that lens pops right out. I can just like clean it like I'm cleaning my glasses. Take it to my shirt. Just like, all right. Where's my pins? There we go. Okay. And we're doing 2.3 and 2.4. 2.3 is on other graphs. So ones that you might see. One is I will show you how to do them in StatCrunch and show you what they look like there. Towards the center too. If I go in too close, then I'm moving the page. Someone's always telling me I don't have enough page on the screen some direction. Either I'm too far up or I'm too far down. Hansel doesn't bite. He looks like he does. Oh, she's like, nope, I ain't getting anywhere near him. He looks shifty to me. Now that I mentioned cleaning my glasses, I realize how much dust is on them. All right, so first chart or graph we're going to look at is called the stem and leaf plot. So I'm going to theorize a bunch of people's ages in the room. I know Sebastian's not here. He's like, fuck it, I don't need to show up for your shit. This shit's easy. Let's say these are the ages of some people in the room. 17, 18. We'll say there's a couple 18-year-olds and 19-year-old. Rather than taking up the whole page with it, I'll do some more over here. 20, 20, 21, another 21. Fuck it, another 21. 23, and we'll have like a 28, and we'll stop there because no one in here is over 30. Y'all look super young. I'm leaving it there. Just hey, just let it go. All right. So what the stem and leaf plot does, actually, let me add some more in. Let's add a couple more 23s. We'll put in 4 23s total, and maybe a couple 29s. And I'm off the fucking screen. You gotta tell me this shit. All right. So, stem and leaf plot. What we're going to do is the way the stem and leaf plot works is it goes, okay, we're going to use the first number or first 2 numbers if it's like a 3-digit number, and that's our stem. So my first digits available are 1 and 2. I've got 1s and 2s. So the way they organize the data is they will put a 1 and a 2, and they'll do something like this. Or they might use a colon instead of a vertical line. And then they're going to do this. This is a stem and leaf plot. Where did I get those extra numbers? It's the second digit, it's the last digit, right? It's the second digit. So this has a couple pros and cons. The pro, a huge pro, it summarizes the data without losing data. I can tell that there's 4 entries in that 10s range. And if I counted them up, I got 5, 6, 7, 8, 9, 10, 11, 12. I got 12 entries. I got more entries in the 20s range than in the 10s range. Okay, so it gives me some form of summary. But if I need to, I can pull this shit apart and get all the ages back. Because the stem and leaf plot doesn't change anything. It just splits the first digit from the second. Sometimes, rather than doing this way, they might do the 2 like this. They'll do like this. Where they'll break it up into 2 rows. Or more. Because there was a lot of entries. You know, I just realized that anybody in this room, especially if you're sitting in the back but can't see well, you can log in on Zoom in the class and have it right in front of you on a computer. Every desk has a computer, even if you didn't bring your laptop. That way you can have like this screen up there right in front of you. I know because my dean did that today in a math department meeting. We were all in a meeting. He was present physically in a computer room and I was on Zoom. And all of a sudden I see his ass pop up on Zoom and I said, oh, look, the dean's lurking. He didn't say anything. And he's like, yeah, I can't see well from back here. I'm like, I'm going to tell you what I tell my students. You can't see from the back row, move your ass to the front. And he laughed, but I realized that's not necessary in a computer room. Just go to our Canvas, go to the Canvas shell and click on Hefe Zoom room and I'll take you right to it. So you can see if you're in the back row. Or over there and you want to pop up the screen, you want to linger on the wall because I know that's your spot. I know you don't like where you're at right now because your spot's over there. She's like, this is not right. I'm not right here. But you can do that. The little hooks on the things, they pop up, screen comes out, keyboard comes out, it's all there. So you don't even need to bring a laptop. So this summarizes the data, but not completely. Like I still got to count them up. If I want to know how many people are in the 10s range, I got to count them up. Another con of this, the biggest con is that this sucks, like really sucks for large data sets. Imagine doing this with like 700 entries on that motherfucker. Especially if you don't have a lot of stems. This is called the stem. The things on these are the stems. And these are the leaves. I don't know why they're not called branch and leaf. It seems like stem to, or stem and petal. That would work because that would be flowers. I don't know. I didn't name this shit. If I could go through and rename a lot of shit in math, it would be renamed. It would be Hefe's way. And then everybody would go, wow, math makes sense. I don't know why I hated it so long. It's glorious. Why didn't we have Hefe's way before? All right, so that's the biggest con. You got a lot of people, it sucks. Like you're gonna have like, especially if I did age with students, you know how many 17, 18, 19-year-olds I get? I'm going to be having a 1 and then like a metric ton of 7s, 8s, and 9s following it. Maybe a few 6s in the front. It does keep them in order. Notice that. So you don't jump around it. They're like sorted in order. So there are benefits to it. But it is one way of portraying data. And you don't lose it. That's the good thing. When we do a histogram, we get blocks, but we don't know like what numbers were in the blocks. Like when it does a bin, we don't know which numbers go in the bin. Let's see. Let's take a look at one. Go to Stat Crunch. Look at Desiree outing her age. You go, Desiree. No, you're not. You're 29. You're right. That's what my wife tells me. No, she does. She's not one of those that lies about her age. Some people lie like after 30, they're like done, like they stopped aging. The fucking wrinkles tell me otherwise. All right, so let's see. I can do it on age. Let's see what happens when I do the stem and leaf plot on age here. Shit, a 14-year-old signed up on this. Look at that second line for 1. Like even figuring out how many 18s and 19-year-olds I have. You know how hard it is to count the same number when it's like a bunch of them in a row? You like literally gotta, like, especially if it's on a screen, I gotta like put my cursor over it as I'm counting them. It's a pain. So it's harder to use when you've got large data sets. But you do see stuff like this, and some of them go like, if there's an outlier, like I had a 79-year-old sign on do this. They're well outside the range of everybody else. So it just like, it put them off to the side. They didn't get a special stem. They're like, you get to be your own plant. We're not fucking with you. We'll just leave you alone. That's the stem and leaf plot. How does it work on height? We go options, edit. So height gives me a good one. It's got them broken up into, these are inches. So the 6 is broken up, the 7 is broken up. And right away, it tells me there's a bunch of people that didn't follow the instructions because no one is 5.11 inches tall. That's pretty short. A $6 bill is 6 inches, a $6 bill. A $1 bill is 6 inches long. So like 5.11 is shorter than a dollar bill. That's not right. That's not someone's height. They've entered their feet in inches. So it can help you spot bad data too. Let's see. So histograms, I told you histograms are the things we're going to use the most in this class. So I want to go over some common shapes that histograms take. Common shapes for histograms. And this is important. You're going to be like, this is not important. And I'm telling you, you're going to need to know this shit for later on. Like whether or not it's one shape versus another changes what you do. So you need to know. So the one we were doing, where we had ages, I had tall stuff on the left. And it started going down as it went to the right. And let's do another example where the tall one's on the right, because that occurs. These are called, they are both on the screen, good. These are the skewed graphs. This is always opposite of the way I want to say it. It always is. The way I look at it, my brain says, where's the largest stack? That's the side it's skewed on. That's not true. It's skewed where the short shit is, or this is called skewed right. And this one's called skewed left. SKEWED. Now, if I were to draw this, I'm going to do little pictures for each of them. The one I just did, if I put like a curve with it, like I put like a curve going down the top, it's like that. Sometimes it's a little there, it starts low, but then it goes really long on the right side. Nope, still skewed right. As long as the right side's much longer than the left. It's arbitrary at some points. Because at some point you get like the hump looks close in the middle. And well, we got ones where the hump's in the middle. So I guess I didn't need that third one after all. So it can either be perfectly like the hump, the largest thing is on the left, or it could be like this one where there's some small boxes, it gets large, and then we've got a lot of short ones going to the right. This one went like that. But it could go like this. With like, you know, just a couple tall ones on the right, and then most of the ones on the left are short. These are called skewed left. So things that are skewed right. Household income. Most families are on the poor or middle range with very, very few wealthy people. The 1%ers. Housing prices. For the same reason, pretty much. You got a lot of middle class homes, there's some shanties and shit like that, and then you got a few of those. This is the $10 million home. You're like, get the fuck out of here. Who's paying $10 million for a house? Number of children. Lots of families only have 0, 1, or 2. Every once in a while, you hit that family that's got double digits. And you're like, God damn, poor mom. That's a lot of birthing. I hear that shit hurts. I don't know. I'm glad on that one. Thanks for taking one for the team, ladies that are mothers. Anyone else think of any? Things that there's a lot of that are low value, but not very many of where there's a high value. Maybe winning lottery tickets. I just came up with that one right now. I need to add that to my book. There's a lot of people that hit the 0 or 0, you don't get paid. I guess on that winning ticket. Where does the winning start? 3 numbers, you match 3 numbers. There's a lot more 3 numbers. There's very few 5s, if any, and like once in a blue moon, all 6. Lottery tickets here. The ones that are skewed left, things that are all mostly high, but there's some lower ones. GPA at graduation. Most of the people that graduate college are in that 3 to 4 range. There are several in that like 2.5 to 3 range. There's fewer in the 2 to 3 range. The closer you get down to 2 and stuff like that, or even below 2, you end up having students that either got C's in all their classes, which can be very frustrating while you're doing it because it means you're having difficulty, or they failed a few times and they just give up and don't make it to graduation, so they never show up on the list. The next one's really kind of fucking sad, but age at death. Most people live to a nice, healthy old age. Some people die, in their middle ages, shit like that. We have a few infant mortalities over here on the left, which is, that's kind of sad when you're like, oh, a 6-month-old died. They had their whole life ahead of them. And then you're like, sad for the parents. Let's see, anything else that's high, but very few lows? Normally I throw like weight in a different category, but I'm betting weight goes in this category nowadays. I bet we're skewed left. America, there's a lot of heavy American, like not slender or ideal weight Americans. We tend to lean on the right, but I'll pretend that it's not in that category. I can't think of any other. Those are the skewed graphs. Any questions on those? Oh. For these, we haven't discussed mean and median yet, but for the skewed graphs, the further they are from the mean is further from the hump than the median. And that applies to both of them. So that means like the mean's over here for this one, and the median's here. Mean is average, and median means middle. Kind of like the median of the road is the middle of the road. So it's like if you put them in a numerical order and just pick the one right in the middle. That's the median. Well, we'll do more stuff with that in chapter 3. I did want to point it out though. So for like the skewed right, since histograms get larger as we go from left to right, it means that the median is less than the mean. Another way of writing that same thing is saying the mean is greater than the median. And I think there's a question in the homework that asks you this, which is why I'm specifically pointing out the symbols with it. Here is skewed left graph. The mean is less than the median. It's the other way, the mean's on the left, so it's less than. Or I could say the median is greater than the mean. I'm in a blurry spot. get something downloaded that I need in a second. All right, you guys ready for the next set of graphs? Always a troublemaker. Last class, girls just about where Hansel is, but the lazy teacher's chair is on the right side of the room rather than the left. But the same distance remains. Like this is like for like a while, like a couple of minutes, and I finally stopped and do I have something on my face? Why are you staring at me? Oh, sorry, I was daydreaming. I'm like, oh, that is much better than the awkward stare. You know? Like, did I have a fly on my head? And you know, did I leave my fly down? You know. All right. Are you good? All right, wait, I didn't ask. Are you good? No, I see the pin still going. You sure?
I am, yes.
Are you? Okay, so our next comment, our most common graph, is what Hansel was asking about. The one where there's a hump in the middle. So our tallest boxes are in the middle. And as we go out to the left, we get shorter ones, but it's about the same amount to the left and right. This is not called skewed middle. That doesn't make any sense. Skewed means something's off, and here everything's just peachy. So this is a symmetrical graph, and it's called bell-shaped. Or a bell-shaped curve. Now, sometimes the left side might be a little bit longer than the right, or the right side might be a little bit longer than the left. But if you have a hard time, like if you're going, should I measure these to see which one's longer? It's probably just bell-shaped. Graphs that are skewed tend to be noticeably skewed. One side's got a longer thing than the other. These sides are called tails. So on the skewed graphs have longer tails. On the side they're named after. Bell-shaped doesn't. Things that fall into the bell-shaped category, types of data sets. Right? There are a few people that are diminutive and a few people that are like Shaq dunk ball, but most people are in that nice 5 to 6 foot range. You closer to 5'6" to 5'9". And then the closer you are to that range, the more there is. And as you get further from that height, the less there is. Weight is in this range. There's a few people that you're like, God damn, eat something. You know, like they look anorexic, like they look like the crib keeper, like it's just bones. And there's a few people like me that like really like to push the weight limit. But most people are like right around like the average weight, maybe a little bit above, maybe a little bit below. I'm what they call an outlier on the weight limit thing. We'll cover outliers later. Intelligence or IQ falls on this list. In fact, IQ is defined off of this list. They put shit to a bell curve and the average IQ is 100. You do it online nowadays. They used to do it in person.
Like random sites, so like have like IQ tests on. I don't know if they're like accurate or.
I'll give you the one from the source, this course. It's called the Binet-Stanford test. We'll cover it later. It's where the IQ test was officially developed, and you can take the test there. And it's just a bunch of math and English problems. So it's like if those are your weak areas, but you're really fucking gifted at other shit, it makes you look like you're an idiot. So IQ tests aren't the best thing. There's other tests that test you in like 8 different categories, and ability to manipulate numbers is just one category. And we'll talk about that later. Anything else that anybody can think of that might be bell-shaped, where there's a lot of things that are average, but not a few that are like large or low or tall? GPA in general, yes. GPA at graduation is skewed, but GPA in general, it's still probably skewed, right? Most people have 2 to 4. Very few people are like below 1. It's like you just quit right away and you don't tally up that list. But it's possible. Maybe. I don't know about this one. I think Hansel's making shit up now the more I think about it. Anything else you guys can think of?
What about shoe size?
Shoe size, I think that's a good one. In fact, let's check it. I got shoe size data right here on the screen. Let's check shoe size. So I'm going to do a histogram on shoe size. Yes, it's tall in the middle and the sides are off. We have the option on a histogram to apply a distribution. And if I put the normal distribution, which is what the bell shape is, it kind of follows the red line. Not exact, but it sort of follows the red line. If I look at age, see the same thing with age while I have it up. If I do this distribution and edit it, oh, it doesn't let me choose one of the normals or the skewed. They're like, if you can't tell a skewed when you look at it, get out. So notice how like there's a bunch that are on the left, but most of them, there's a lot going to the right. Whereas this one, the humps in the middle and there's shit to the left and right. The skewed ones, sure, there's some shit over here. That's the 14-year-old. But most of the shit's to the right. That's what's meant by skewed. And then there's the one. Anything else? Shoe size is good. I think I want to add that. No, I talked about mean and median, the other one. On a bell-shaped curve, it tends to be both. Mean and median are in the same spot. Is everybody ready? Do I need to leave this alone? Yeah. I know who to ask. I got one person that likes to have accurate notes and is thorough. That's the polite way of saying takes a while. I'm teasing you. Last one. Is there a hump here? There's no hump. This is called the uniform distribution. All of these things are called distributions. The skewed left distribution, the skewed right distribution, the bell-shaped distribution. And I will cover that, all those terms more again later. Things that fall in this category are generally where everything has the same chance of happening. So where does this happen? Like with rolling a single die. Die is single is one dice. Most people say dice and don't know that die is singular. Drawing a card from a deck. Deck of cards. There are 4 suits. And if we just pick random cards and throw them in the stack of the suits, we'll have about the same minute when we've done a bunch. There are 13 called ranks. Ace through king. So ace, 2, 3. How many people have never seen a deck of cards? I bet Sebastian hasn't. He's not in here. So everybody's familiar with the deck of cards, like the hearts, the spades, the clubs, and shit like that. Whether you've played with them in a long time, as long as you know what they are, this will make this semester a whole lot easier. It's like when I hit probability, I like to use cards. I bring in cards, and every once in a while, I know I'm gonna have to show Sebastian. I know he doesn't fucking know what they are. Actually, he's just one of those smart high school students. He might have played around with them. Solitaire games, shit like that. It's where like the probability of everything happening is about the same. They're not skewed. There's no real middle. I mean, we could find the middle by putting them in order and just picking one, but it's probably right, right in the middle of the picture. The mean is right in the same spot. There's nothing exciting with the uniform thing. Those are the different types of distributions. So distributions that are the common ones, we will do other ones, but the 4 major ones are skewed left, skewed right, the uniform, and the bell-shaped or normal distribution. It's got 2 names. The bell-shaped one is the most common one, and so that's why they call it the normal. You guys ready for more? I'm going to write a statement. Of 1,000 people surveyed, 1,000 people surveyed, who have played Russian roulette. all 100% of them have claimed that they survived the game. Thus, Russian roulette is completely safe to play. I think I could think of a particular Russian leader that should play Russian roulette for a while. I think the world would be a little bit better place without Putin in there. Just tell him it's a fun game. It's called roulette. You'll love it. He's Russian already, so we don't need to add the Russian part. Let's play roulette. What's wrong? Go ahead.
No, it's because you really keep Russian.
I don't know. I have no idea. That'd be a fun thing to look up. What's wrong with this statement? What's misleading about this statement?
That is safe to play.
What?
That is safe to
So this is misleading because it says it's safe to play.
Yeah, survey the people who died.
And I want to argue, but all 100% said they survived. Not a single one died in it. How can those people be wrong? For those of you that are unfamiliar with Russian roulette, you don't load a full gun, you spin the revolver, you put it to your head, you go click. And the first person that, or the last person that's standing wins. Everybody else loses the hard way. Generally, I don't know. I'm not familiar with, I'm not a contestant in the Russian roulette. I would think they just leave, like put one bullet in and then do it. And then once one person's done, then they reload the next bullet. Sometimes it's only played with two people and they just go back and forth. I don't know. I don't know of anybody that does this. This thing's like some like, I'm gonna kill you if you don't do this thing, like Saw. This is some Saw shit. Like, or I'm gonna kill your entire family kind of thing if you don't do this. And then you're like, I love my wife and kids. I'm okay, I'd rather protect them. But the point is, Russian roulette kills most of its contestants. So what's misleading about this is that the way it's designed mislead people. With our statistical analysis. And I completely spelled analysis wrong. This is bothering the shit out of me. Give me a minute. What the fuck does this thing do? Other than blur it up? It looks fine. God damn it. Is that what I need to do? Just start popping these out? I have no idea. Like this thing is, I don't know what it does. It's definitely clearer now, but that just might be because this is dirty. I know. Fuck it. If all I gotta do is slide it out, I can do lectures like this the whole way. Good to know. So I'll show you guys some stuff that is misleading that you want to avoid. and I will show you where I got it. So if you go to your Canvas course and you click on files, there is something that says Math 21 lecture notes in class docs. So if you want to have this right in front of you on your screen or look at it later, I will reference it on and off again throughout the semester, especially when we get to the last half. There's a lot of good hypothesis tests in there. I already downloaded it. Okay. A lot of ways we mislead people or people are misled with statistics is through graphical representation. Okay. So this graph right here, it says the following time series graph was created from the given historical data on life expectancy. What is misleading about the data and what might be a better way to draw the time series? So if I look at the graph without looking at the data, the left says 1950, the right says the year 2000, and the left is really, really fucking low on the graph. And the right is really, really high up, and this is life expectancy. It looks like from 1950 to the year 2000, we got really fucking good at saving lives, like super good, like taking it way end of the 1950s side. When you look closer, though, this starts at 68 and goes up to 78. And we can see that over here in the numbers, 68 to 77. So yeah, they've added almost a decade to the average lifespan. But does that graph look like it's saying it just adds, 9 years? If you just look at it, I hope not, because it doesn't to me. It looks like the left is really, really low and the right is really, really, really high. What the problem with this graph is it's not showing the dead space that people like to do. If I were to draw this graph realistically, 1950 to year 2000, without having all the dots, 68 and 78 would be like this, and it's like something like this. And the graph's up here. And they're like, that's a lot of white space on the page. That's a shitty graph. So we're just going to shorten it, make the 68 right here. That's what they did. They did the 68 there, the 78 there, and now it looks like really distorted. Here, this is a lot lower than that. This is like 3 times larger than that. But if I go up to the big picture, it's only like 10% taller. So visually, it looks like it's a lot more. The ways we can do that if we've got graphs, is you gotta have to do a little graph editing. If you want to have that start at 68 and go up to like 78 over here, and you got your axis over here that's got like 1950 to 2000. If you're not starting this vertical line at 0, put like a squiggle there. And now doing it, even though the graph looks a hell of a lot taller on the right, the squiggle captures the eye, catches your attention. If anything, it might make you look at the numbers, which you may not have looked at in the first place. Most people don't. You look at the way the graph is shaped. The way is the line going up? Is the line going down? Is it going up a lot or a little? Squiggle catches your attention and it can point out there's a gap. I've got really one more I want to show you, and then we're gonna be done. Told you this day is gonna be short. Back to the, wait, anybody writing this? Yeah. Please write, we got plenty of time. I will make everybody wait till 7 o'clock. I'm good. Everyone ready? Are you still ready?
Me? Oh, no.
I can see your pen going, so I don't know if you're doodling or whatever. What is your name? I forget.
Linda.
Or Linda. Okay. All right. This picture here is a pie chart. Says the National Survey of Student Engagement is a survey that, among other things, asks first-year students at liberal arts colleges how much time they spend preparing for class each week. The results from the 2000 survey are summarized to the right. The given pie, well, it's not on the right, it's on the left. This given pie chart was constructed from the data. What's misleading about the pie chart? So let's not look at the data right now. Let's just look at the chart, see what we're seeing. I see which color looks like the biggest color. The one in the front, right? This one right here? Where's my mouse?
Yeah.
This one right there?
Yeah.
It looks like that one corresponds to the 6 to 10. And like the purple and the green, they look a lot smaller, don't they? The purple is the 1 to 5 or the 11 to 15, the green is 1 to 5. Let's come over and look. The 1 to 5, the green is 13. The beige is 25%. So 13% and 25%. So the green is about half the size of the beige. And so maybe it should be a lot smaller. When I look at the purple though, the purple is 0.23 or 23%. If you were looking at a normal picture, do you know that you'd be able to easily tell the difference between 25% and 23%? Probably not. Not unless it had like 4 exact 25% pieces, and then you saw that one of them didn't make a perfect thing, then you might call like, this is bullshit, one of them is not 25%. But if you're just looking at a pie chart, it's gonna look pretty close to a quarter of a circle, the 23%. Here it doesn't. If I look at the 16 to 20, 16 to 20 is the yellow. It looks even smaller, but it's still almost 20%. What 3D pie charts do is overemphasize the segment that's in the front. Don't do 3D pie charts is the takeaway from this. They're fun to look at, but they're completely misleading. The wedge in the front is overemphasized. Like if you look at it, it looks more like a third or 40%. Not 25%. It looks like a lot more than 25% when you look at it the way it is. That's kind of it for chapter 2. So you have 2 choices. Well, you have a lot more than 2 choices. But the primary 2 are you can hang out here, work on home. Or option 2 is you can get the fuck out, have a good weekend. And that you are free to roam about the country. Yeah, you walked out like 3 minutes early. You had no idea, did you? This is how all my Zoom classes are gonna end this semester. The video is gonna end with me telling the students to get the fuck out. This is someone's gonna think I'm a terrible teacher.